For section 21, polynomial function analysis, we're going to be describing the behavior of the graph of a polynomial function, and then we're also going to talk about the end behavior of a polynomial function with relation to the limits. So for our entrance slip, it says given the graph of the quadratic function h of x below, it says on what interval is h of x increasing, and then on which interval is h of x decreasing. So you can figure out where h of x is increasing or decreasing based on where the graph is changing. So my graph is changing at this point right here. My graph starts at the top, so we always read a graph from left to right, and it starts by decreasing. So an interval is in between two x values. So for the interval, we're starting at a decreasing. So I'm starting to decrease from negative infinity until we hit negative 3. So when x is negative infinity until x is negative 3. That's the interval at which h of x is decreasing. Now h of x is increasing starting at negative 3. So starting at negative 3, and it is increasing forever and ever as positive infinity. So as x approaches positive infinity, my graph is increasing. So we're going to use increasing and decreasing, and that denotes the behavior of the function. So we have two examples. So we're going to be talking about intervals of increasing and decreasing. So we always read a graph from left to right. So I'm going to put a dot right here on the left side of the graph. You can think of this as driving a car. So starting at this point, as I'm driving a car, it would be going up a steep cliff. So we're going upwards, which means that I'm increasing. Then we get to the top. Once I get to the top, now my car is going to be going downwards. So now I'm decreasing until I get to this point right here. At this point right here, we're switching again to increasing. So my behavior is increasing, decreasing, increasing. Next one, in example 2, I'm going to put a dot at the start of my graph on the left side. We read graphs from left to right. So we're driving a car, and I'm going downwards. And as I'm going downwards, I hit this point right here, and I switch directions. At this point, now I'm going upwards, which would be increasing. And I'm increasing until I get to the top. And then I begin decreasing again. And I'm decreasing until I get to the bottom once again. And then we end by increasing. So we have decreasing, increasing, decreasing, increasing. Now the points at which my graph is changing, that's called the relative maxima and the relative minima. So the relative maximum is the point in which the function is going from increasing to decreasing. It's called a maxima. Then we have a relative minima. This is the point in which the function changes from decreasing to increasing. Now, in example 1, we have a maxima. We only have one, and we only have one minima. In example 2, we have one maxima, and we have actually two minima. Okay. So just to start thinking back up to section 20, in section 20, we learned about the leading coefficient being the end of the graph. So in example 1, my leading coefficient would have to be positive. In example 2, my leading coefficient, again, positive. So don't forget about that from section 20. We're going to go ahead and do numbers 1 through 6, and we're going to be writing down the behaviors, so increasing or decreasing, increasing, decreasing, as many behavior as there are. We're going to write down the number of relative maxima, the number of relative minima, and then the degree of the polynomial. The degree of the polynomial has to do with how many times your graph touches the x-axis. None of my graphs will have any complex zeros, because obviously we don't graph those. So no complex zeros in each of these. Here we go, number 1. So I'm going to put a dot at the top of my graph, and I'm going downward. So we're going to start by decreasing. Backslash, I get to the bottom, and then my graph begins to increase. So we have decreasing, backslash, increasing. Now in this problem, we don't have any, so we are going to write 0 maximas. However, we do have 1 minimas, and I have 1 2 zeros. Since we have 2 zeros, 2 times in my graph hits the x-axis, 2 is my degree. In number 2, I'm going to put a dot at the end of my graph. We start by increasing. I increase until I get to the top, which means that I have one maxima. At least one, and there is only one. And once I get to the top, then I'm going to begin to decrease. So we have increasing, backslash decreasing. There are no relative minimas in this problem, and then the degree of the polynomial is based on my x-intercepts. There are 2 x-intercepts, there are 2 zeros, 2 x equals, so therefore my degree is 2. You want to go ahead and try numbers 3, 4, 5, and 6, and then we'll go ahead and come back to talk about the leading coefficients of each of those. Go ahead and check your answers to numbers 3 and 4. Notice that both of these had a degree of 3. My relative maxima for both of them was 1, relative minima was 1. In number 3, we were increasing, decreasing, increasing, and then in number 4, we were decreasing, increasing, decreasing. In number 3, my leading coefficient, so we're ending up, so the leading coefficient is going to be positive. In number 4, my leading coefficient has to be negative because I have a downward arrow on the far right side. In numbers 5 and 6, both of these had a degree of 4. My relative maxima for number 5 is 1, relative minima for number 5 is 2, and my leading coefficient is going to be positive because it's going up at the end. In number 6, we have a degree of 4, relative maxima 2, relative minima 1, downward arrow, so therefore my leading coefficient had to have been a negative number. Now, take a look at these. Numbers 5 and 6, the degree was 4, and I have 4 behavioral changes. In numbers 3 and 4, my degree was 3, and we had 3 behavioral changes. And then in numbers 1 and 2, my degree was 2, and we only had 2 behavioral changes. So we can say, based on this information, that the relationship between the behavior and the degree is that they're equal. Now, comparing the degree to the number of relative maxima and minima combined, when the degree was 4, combined, they were 3. When the degree was 3, combined, they were 2. And then when the degree was 2, combined, they were only 1. So we can actually form a relationship between the degree and the number of relative maxima and minima combined. So if I take the degree and subtract 1 from it, that's how we get the number of relative max or min. Or we can go the opposite way. The number of min and max plus 1 gets me the degree 2. 2 ways of writing the exact same thing. So based on those answers, if my degree is 5, which means that we have something x to the 5th power, the total relative maxima and minima has to be 1 less than that. So we would say that it's 4. In number 10, the behavior of a 6th degree polynomial, so that would be x to the power of 6. And let's say that it begins with increasing. Now, knowing that the degree is 6, that's equal to the behavior number. So if I start increasing, then I'm going to go decreasing, and I have to do this 4 more times to get a total of 6 behavioral changes. And then in number 11, we have a quartic polynomial. That would mean x to the power of 4. Says how many total relative maxima minima are there? Well, it'd be 1 less than that, which makes 3. Now we have the impact of double zero. So we're still talking about behavioral changes and the number of relative max and mins. So if I go ahead and take my pen and every single time that there's a double zero, I can put a dot and a D. All right, so those are all my double zeros. Let's take a look at this 5th degree polynomial function. Now for a 5th degree polynomial function, my behavior should be 5 behavioral changes. So we read our graphs from left to right. I start by increasing. Then I get to the top. When I get to the top, then I start decreasing. So that's 2. Then I get to the bottom. Then I start increasing. That's 3. Then I get to the top again. And then I go down to decreasing. So that's 4. And then finally, I'm going to go up to increasing. So we have 1, 2, 3, 4, 5. So the behavior's 5, which matches the degree. So even though we had a double 0 there, this has no change on the behavior of the function. Let's go back to this 5th degree polynomial and talk about the relative max and mins combined. So if my behavior is 5, my degree is 5, so the max and min number should be 4. Now as I went along, we have 1, 2 maxes, 1, 2 mins, which means that it's true. It was 4, like it should have been. So even though we have a double 0, it will have no impact on the number of relative maximas and minimas, even though there's a double 0 there. So we can still use the relationship between the degree and the behavior and the degree and the relative max and mins as a way of figuring out each function.